So we're going to look at some linear and quadratic patterns and use their first and maybe second differences to come up with the recursive equation. Now, we've practiced the linear recursives to death. Those should be simple, automatic for you. The quadratic ones are still pretty new and they're more difficult, so that one might challenge you. From negative 23 up to negative 17, here number one is going up 6. Then up another 6, another 6. So in this one, this pattern is linear since it has a constant rate of change. So our formula is, again, we always have to come up with some place to start. So f of negative 3 is negative 23. And the next f of x is found by adding f of x minus 1 plus that constant rate of change. And number 2, pattern, this one goes down 4, then down 2, then none, then up 2, up 4, and up 6. Well, that's certainly not linear. It should be quadratic. Let's do our second differences to verify. From negative 4 to negative 2 is 2, then up another 2, up 2 more, and yes, this does fit the pattern of quadratic functions. Because our first differences are linear, these numbers in red form a linear pattern. The black numbers over here are a constant. So the second difference is constant, or the first difference is linear. All right, so I still need some place to start. F of negative 3 is 4. To get the new f of x, go back to f of x minus 1, and then add. Now remember, what we add out here is a whole expression in the form of mx plus b. Now the m comes from this 2 that was our constant second difference, but the b is really just an adjustment that you make. So here's how we have to go back up into the table where you know 2 successive terms, like for example, to get from first to second, and try it. To get f of 2, I would go back to the value of f of 1, which is 0, and add 2 times 2, so that's 0 plus 4, or 4. Is f of 2 4? It is. So I don't have to adjust this one at all. There doesn't need to be a b term added after the 2x. Number 3, from negative 15 to negative 10 goes up 5. Negative 10 to negative 5 is up another 5, and so on. So this has a constant rate of change. This one is linear. F of negative 3 is negative 15, and a formula f of x is f of x minus 1 plus the constant rate of change, 5. Number 4, 24 down 2, down another 2, down another 2. So we see linear again with this constant rate of change. The recursive equation, f of negative 3 is 24. Any new f of x can be found by adding f of x minus 1 and a negative 2. Number 5. From 48 to 22 goes down 26. 22 to 6 goes down 16. Then we're down 6. Then we're up 4, up 14, and up, what is that? That's 24. So we have a linear pattern in our first differences, and our second differences just keep adding 10. So once again, what we're seeing here is a linear first difference in purple or a constant second difference in orange. Either way, we call that a quadratic function. And make our recursive equation. F of negative 3 is 48. Any new f of x, we would do f of x minus 1 plus, again, from here, plus 10x. And now let's see if we need to adjust. Well, by adjust, choose two successive terms up here and say, all right, if I were looking for f of 3, I would go back to f of 2, that's 18. I would add 10 times 3, so that means I would be doing 18 plus 30, that's 48. Is f of 3 48 in the table? Well, no, f of 3 is 42. So how do I adjust that? I need it to go down 6. Right? If I had that adjustment here, now I get the desired 42. Number 6. 4 to 1 is down 3. 1 to 0 is down 1. Then up 1, up 3, up 5, and up 7. So there's our linear first difference, which will be followed by a constant second difference of positive 2. So we have quadratic again. And our recursive equations start with f of negative 3 is 4. Then f of x equals f of x minus 1 plus. Now our y, or our mx plus b little expression here begins with plus 2x, and I see if I need to adjust it. Well, if I decide I'm going to use these two, I would say I'm trying to get f of 2 by taking the value of f of 1, that's 4, and adding 2 times 2. That's 4 plus 4, or 8. Is f of 2 8? No, f of 2 is 9. So I need to adjust that by adding 1 to get my 9. So that means in my formula, it can't be just 2x. I need to adjust it up 1. Okay, number 7. We are predict the number of squares in figure 30. Well, we're only up to figure 4. Okay, I'm sorry, we have to draw figure 4 and then predict the number in figure 30. Model what we did to get that. So that's show me your work. Okay. So what I see going on in each of these, if I split this into sections, in this first one, or in all of them, I have little square, one on the bottom left and one on the top right. Okay. And then I have a 1 by 3 rectangle. In this one, it becomes a 2 by 4. In this one, it becomes a 3 by 5. So following that pattern, my inner large rectangle here would need to be 4 by 6. So I need it to be 6 boxes tall and 4 boxes wide. Okay, and then add back on my one on the top right and one on the bottom left. Now, what is the total number in each of these then? Well, again, if this is a 1 by 3, that's 3 boxes. Add 2 more is 5. 2 by 4 is 8. Add 2 more is 10. 3 by 5 gives us 15. Add 2 more is 17. My 4 by 6 is 24. Adding these two is 26. So what kind of pattern is showing up here? Well, that goes up 5, up 7, up 9, and I end up with a quadratic pattern. My constant second difference is 2. A quadratic pattern. So I need to extend that all the way to figure 30. Well, I'm certainly not going to draw those, but I could tell you what figure 30 would look like. If I go back to these dimensions that I came up with, on figure 1, that inner rectangle was 1 by 3. On figure 2, it was 2 by 4. So the first number in each of those dimensions is the figure number we're on. All right, 1 by 3, 2 by 4, 3 by 4. Its longer dimension is just 2 bigger. So 2 bigger than 1 was 3, 2 bigger than 2 was 4, 2 bigger than 3 was 5. So if I went to figure 30, it would have a 30 by 32 big rectangle plus one on the top right and one on the top bottom. So 30 times 32, if I multiply that, is 960. That's how many little boxes would be in the large rectangle. And then add 2 more. So 962. So that's one way to model it. If you have a calculator handy, you could do quadratic and come up with a formula that you could just substitute 30 for your variable, your x or your n. Okay. Now, one more thought. If I had this model visualized in my head and no calculator, how can I make a formula for this? Well, let's think. The dimensions of this box were always whatever figure I'm on times that same number with 2 added to it. And then after I figure out the number of boxes in the big rectangle, I added 2 to the end of that. So here's a formula. We could simplify that with the distributive property if you felt like it. If you actually used your calculator, your formula would look more like this: n squared plus 2n plus 2. And then you would just say, well, I need f of 30, so that's 30 squared plus 2 times 30 plus 2, or 900 plus 60 plus 2, which again gives me the 962. And we want to look at these recursive equations and come up with the first 5 terms. Okay, so f of 0 is where I'm starting, but my first 5 then would be like 1, 2, 3, 4, 5. So to get f of 1, this formula tells me go back to f of 0, well that's -5, and add 8 to it. So -5 plus 8 is 3, right? So we took where they told me to start, -5, and we just added 8. So to continue, I just need to keep adding 8. F of 2 would be 11. F of 3 would be 8, or 8 more is 19. F of 4 would be 27. And F of 5 would be 35. Now that was for a linear one. Number 9 is another linear one. This time it says, though, to subtract 5. Well, if f of 0 is 24, f of 1 would subtract 5 from there and get 19. F of 2, subtract another 5. F of 3, subtract another 5, and so on, giving me, subtracting 5 is 4, and f of 5 is -1. Now, numbers 10 and 11 are exponential because we're multiplying by 3 and multiplying by 2, but same procedure. If f of 0 is 25, I want to multiply that by 3, so f of 1 would be 75. Then I would multiply that 75 by 3, which is 225. Multiply that by 3, that's 675. Multiply 675 by 3, that's 2025. And multiply that by 3, f of 5 is 6,075. And one more. Number 11, we're starting with 6 and then multiplying by 2. So f of 1 would be 12. Multiply that by 2, 24. By 2 again, 48. By 2 again, 96. And by 2, one last time, 192.